Okay, it asks us to approximate the area bounded by the graph of f of x equals x squared on the interval from 0 to 4 using the midpoint rule with 4 rectangles. So, in this graph that we're looking at here, zoom back out a little bit. I have just graphed x squared from 0 to 4, right? So that is the blue graph that you see here. And so rather than having your rectangle hit at the left corner or the right corner, we're using the middle of that section. So all of my rectangles hit at the middle of the section that we're looking at for this. So if I'm looking at how to do this, I'm going to scroll all the way down here. I think I've already done that. Never mind. So if I'm looking at how to do this, my width of my rectangle is still just 1, right? That's I'm going from 0 to 4. I need 4 rectangles. So if I take 4 and divide it by 4, I'll get 1. The width of each rectangle is still 1. But the height is not going to be the left endpoint or the right endpoint. It's going to be the value of the function right there in between, right? So what would be the x-coordinate right here for that first rectangle? 0.5. What about the next one? 1.5. Here we'd have 2.5 and 3.5 for that last one. So whenever we set this up for this problem, where our width of our rectangle is still 1, but we would multiply it by f of 0.5, f of 1.5, f of 2.5, and f of 3.5. You still want to make sure that if you have 4 rectangles, you got 4 numbers right here. You're not using 0 or 4. You're using the numbers in between on your intervals. So it's usually for me helpful because you're usually not going to graph this whole thing. It's usually helpful for me to kind of, if I'm doing this without graphing it, I'm going from 0 to 4. I'm going to split that into 1, 2, 3, 4 sections. And so I know the width would be 1 by looking at that. And then I'm just thinking of using the points in between right here as my value. So that would be my 0.5, my 1.5, 2.5, and 3.5 for this problem. And we're going to use the calculator. This is not a terrible one to do by hand. It's just we're going to move on. If we wanted to do it by hand, so I'll at least show you like what you would do. If you want to do it by hand, f is x squared, right? So you would just plug 0.5 into x squared. So it would look like this. 1 times 0.5 squared, that'd be f of 0.5. And then we'd have 1.5 squared for f of 1.5. And then 2.5 squared for f of 2.5. And 3.5 squared for f of 3.5. So you would just plug those in. So it could, if it were whole numbers, it would be like a calculator inactive type of problem. Technically, we could do this without a calculator. We just need fractions instead, but we won't spend our time on that. If you type all of this in, I think I already put it down here at the very bottom. I did, to save us even more time. And if you type it in, you'll get 21 for that. So that would be our answer.
So is the midpoint be more accurate than the left or right?
It is typically a little bit more accurate because while it is a little bit over here, it's a little bit under here, so it balances out a little bit more. Whereas with the left or the right, especially if your graph fits certain conditions, it's usually everything is over or everything is under, so you're not as close. Whereas this, you can see that little triangle looks kind of the same size as that triangle. So this is typically more accurate, depending on which function you are using it for. So, let's continue on. Okay. Another option that is possibly even more accurate is to do trapezoids. So here it asks us to approximate the area bounded by the graph of f of x equals sine x between x equals 0 and x equals pi. Use the trapezoids with 6 subintervals. And this one is calculator active here. So if I'm going from 0 to pi and I have 6 subintervals, then I am going to need to break pi into 6 pieces. So I'm going to be counting up by pi over 6. So you got pi over 6. This is 2 pi over 6. This is 3 pi over 6. This is 4 pi over 6. 5 pi over 6. And then 6 pi over 6 equals pi. Right? So even though it doesn't quite look like it there, you're just counting up 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and so on. And so with the trapezoidal rule, what we're going to be doing instead of, or with trapezoidal midpoint sums, instead of using a rectangle, we're going to use a trapezoid. So if I draw those in for us here, I have to hand draw these. This first one is a little misleading because your endpoint here and your endpoint here does not actually make a trapezoid. It makes a triangle. That happens sometimes. They're not actually a trapezoid, but it still will work out for us. And then the next one, if I go straight up from this point, if I draw a trapezoid here, I'd have this trapezoid. And then here's the next point. I'd have this trapezoid. Our next point, I would draw this trapezoid. Here, I have a trapezoid. And the same thing happens over here on this last side because of your symmetry here. You end up with a triangle for that last piece. Now, when we were doing left and right Riemann sums, some of those estimates seemed almost ridiculous, right? You had such big pieces that you were missing, right? I mean, like if you look at some of our graphs that we have here, like if you look at that back graph right there, you know for sure that's not right. It's under by quite a bit, right? So, so with left and right Riemann sums, sometimes you are way off, and that's just by the design of it. Trapezoidal is a lot closer because if you look at this graph, we're not off by much. I think it's going to be an underestimate. I think we're under just a little bit here, but it's pretty close to what we get. So this is going to be a better estimate. As seems to be the case with things that are better, it also is a little harder to do than the left and right Riemann sums. It's not terrible, but it's a little more difficult. So one thing we've got to remember for this is the area of a trapezoid formula. So your area of a trapezoid is 1/2 height times B1 plus B2. I hesitated on calling that height right there because B1 and B2 are always your parallel sides. Your height in this case is what we would really call the width right here, because if we were doing this middle trapezoid right here, if we're doing this trapezoid right here, then the bases are the parallel sides, so the bases are the vertical sides. This is your B1, this is your B2, and then this down here would be your height for that. If you want to call it width instead of height in that equation, it's fine as long as you know what you're talking about for this. You can also do base 1 plus base 2 divided by 2 times height. That's an option, or the whole thing divided by 2 instead of times 1/2. So if we look at the first trapezoid, it's not really a trapezoid, but we can kind of treat it as a trapezoid. So I'm going to call this A1 right here. So this first one, I'm going to have 1/2. The height of my trapezoid, which is really my width, here is going to be pi over 6. Okay, because the width of all of these little increments right here are pi over 6, because that's what we were counting by. And then I would have base 1 here and base 2 here for this first one. But because this is really just a triangle, that first base is 0. And the second base is, I know it's 0.5, but I'm just going to call it f of pi over 6 for right now. Sine of pi over 6 is 0.5, so that's what you get. So that would be this one right here. It's a little weird. You could just use triangle formula on it, but I want us to see some structure in what we're doing here, so I've done it this way. And in fact, if I wanted to, I could call this f of 0. Might should, instead of just calling it 0. F of 0 is 0 for this problem. So my second area would be 1/2. The width is still going to be pi over 6. We're going to see that show up over and over and over again because we have equal increments here. So for the second triangle or trapezoid, which is the one I have shown, we are looking at base 1 and base 2 being this point and this point. What do I do to find the height of this point right here? F of pi over 6. And then B2 would be f of what? Pi over 3. Or if you want to call it 2 pi over 6, that's fine. And I guess technically this could be a calculator inactive problem because these are all unit circle values, but we've not got time to make that happen. I used it because I'm wanting you to see some structure in what we're doing here. You could use triangle and it would be fine. You can treat a triangle like a trapezoid where one of the bases is 0. Because if you see what we're doing here, 1/2 times the base of that triangle is pi over 6. The height of that triangle would be the f of pi over 6. And because this is just 0, it doesn't change that. So you can treat a triangle like a trapezoid that has one of its bases is 0. And so for the structure of what we're doing, I'm using that. But you definitely, if you just want to find it, could use a triangle formula instead. You wouldn't even need that because this would be your base right here, and this would be your height. They're perpendicular, so you wouldn't need to know that third side for that one. Okay, yeah, you would just do. Find the area of that rectangle. Right. Okay. So that would be A2 right there. A3 would still have 1/2. We'd have pi over 6. And then for A3, we would have the left side right here would be f of pi over 3. And then the right side would be f of pi over 2. For the fourth one, you can probably starting to see a pattern here. You've always got that 1/2. You've always got that pi over 6. You're going to have f of pi over 2 plus f of, what's next? 2 pi over 3. And if you would rather use 4 pi over 6 instead of 2 pi over 3, so that you're seeing this is pi over 6, 2 pi over 6, 2 pi over 6, 3 pi over 6, 3 pi over 6, 4 pi over 6, it might show up a little bit. That is fine. Fifth one is going to be 1/2 pi over 6. This one's going to be f of 2 pi over 3 plus f of 5 pi over 6. And our last one is also really a trapezoid, triangle, but we can just treat it like it's still a trapezoid. One of those bases is being 0. So I've got f of pi over 6, 5 pi over 6 plus f of 0. Let me look ahead just a second here. Let's see. Where I put that. Okay. Alright, so I've got all of this stuff. It is calculator active. I wish I'd already made a Desmos one where this was done for us. But I haven't. So if our f of x equals sine x, I've got the first one be 1/2 pi over times pi over 6 times f of, I need parentheses here, f of 0 plus f of pi over 6. Oh, gracious. All right, so I've got, that would be my first one. I'm not even going to write that down because so many decimals. Then I would have to find the next one. So I could do pi over 6 plus, let's just do 2 pi over 6, right? Got that one. I got 2 pi over 6 to 3 pi over 6. I've got 3 pi over 6 to 4 pi over 6. I've got 4 pi over 6 to 5 pi over 6. And I've got 5 pi over 6 to, I'm going to just put 6 pi over 6, which is pi, right? So all of those are going to give me my values that I have over here. Instead of write down. I'm going to write down a few. So I got 0.131. I've got 0.358. In real life, you probably should not round all these. You should add the whole things together. I've got 0.489. Then this starts to repeat because this is symmetric. I got 0.489. I got 0.358. And I've got 0.131. So I would take all of those and add them together. So got this number plus this number plus this number, and then I could just take that and multiply it by 2. So if you add all of those together, we should get 1.954. I multiplied it by 2 just because I only did like I only added the first 3 together here. And so since those second 3 are the same, I just doubled it. I was just trying to shortcut it a little bit. So we got 1.954 as our estimate. Now, there will be times when you have to find the area of every trapezoid separately, particularly if you have a problem like we saw on the warm-up where the width of each interval is not the same. You would have to find the area of each trapezoid separately. But it feels like there's got to be a few more shortcuts on this, right? Because we are just, like, everything seems so repetitive. And there is for trapezoids. So let's look at the next question. Even though, did I give a, yeah, this is trapezoid. Right here. Okay, so for this problem, the temperature in degrees Celsius of the water in a pond is a differentiable function, W of time T. The table above shows the water temperature as recorded every 3 days over a 15-day period. Approximate the average temperature in degrees Celsius of the water over the time interval from 0 to 15 by using a trapezoidal approximation with subintervals of length delta t equals 3 days. Here. So this one has a little bit of a trick to it. We haven't done average value yet, or it'd make a little bit more sense. They want average temperature, but this already gives us temperature, right? So because they're equal subintervals, it actually might work to average those. I'm not sure. I haven't tried it. It may work. If they're not equal subintervals, it does not work to do that. But this specifically tells us to try a trapezoidal approximation, so we want to do that. I don't know if it will work. It would if it asked for a left or a right Riemann sum, but for a trapezoidal, it will not. Because I know the temperature on day 0 was 20, but I don't know what the temperature on day 1 and day 2 were. So I'm sort of guessing at what is happening there. So whenever I find the area underneath the curve here, it is going to give me the, like, if you think about what you've got here, you've got days here, and you got degrees Celsius here. So whenever we find an area, we will be doing days times degrees Celsius. That means, I mean, that's not really like that's days times Celsius. That's not degrees Celsius per day. That's those two multiplied together. What that is telling us is it's giving us the sum of the temperatures for all of the days, because we're taking the number of days that we had and multiplying it by the temperature of that day. So the very last step on the end of this to find average temperature is we're going to have to divide it by 15 days. But first we got to do the trapezoidal to get that information in the first place. So if I'm doing a trapezoid for all of these, from a table, I can think about what the graph would look like. But from a table, what is the height of each trapezoid going to be? And really height, we're kind of thinking more width whenever we do that.
3.
It's going to be 3, right? This is your height right here. That's your height. So we're going to have 1/2 times the height, which is 3. And for that first trapezoid, base 1 would be here, and base 2 would be here. So I have 20 plus 31. And I could type that in, but I'm gonna do every one of these, and then we're going to talk about how we can make it easier to put in. Okay. So then if I do the next one, 1/2 times 3 stays the same. What numbers would I use here? 31 and 28. Okay, because that 31 gets used again. That's like the side they share, right? The first trapezoid and the second trapezoid share that side, so it gets used twice. So the next one is 1/2 times 3. And this time, from 6 to 9, we're using 28 and 24. Then we got 1/2 times 3, and we'll have 24 and 22. Next one, we'll have 1/2 times 3, and we'll have 22 plus 21. And that's going to be our 5 intervals. We've got 6 numbers, but we got 1, 2, 3, 4, 5 intervals there. Now, if I'm going to put this all in the calculator, right, because all those have to be added together, I would prefer not to type every bit of that in. So let's reason through what we could do here. So first of all, every single one of these have a 1/2 and a 3, correct? So would it be okay if I just take 1/2 and 3 and I pull it out front like that?
Yes.
Okay. So that would leave me with doing 20 plus 31 plus 31 plus 28 plus 28 plus 24 plus 24 plus 22 plus 22 plus 21. Now, what do you notice about this long string of numbers? Because this still looks pretty long to put in. What I see here is that 31's there twice, 28's there twice, 24's there twice, and 22 is there twice. 20 is only there one time, 21 is only there one time, right? So, if I wrote it like this, it would still be equivalent. I could do 1/2 times 3, and then I could do 20 plus 2 times 31 plus 2 times 28 plus 2 times 24 plus 2 times 22 plus 21. So looking at that table, you use the first number one time. All of the middle numbers you use twice. The last number you use one time. All right? And this will make it a little quicker to type in. And it's going to make it way easier on the next problem. So 20 plus 2 times 31 plus 2 times 28 plus 2 times 24 plus 2 times 22 plus 21. I don't think it likes brackets. Let me get rid of the bracket. Let's do parentheses instead. There. So I'm getting 376.5. And that is days times degrees Celsius, which is a really weird thing to say. But what it means is it's like the number of days times the temperature each day. So it adds together all of your temperatures there. So it is like all of the temperatures for all 15 days added together. But the question did not ask us for that. The question asked us for the average temperature. And so since this is over 15 days, for the average temperature, we would do 376.5 and divide, that is days times degrees Celsius, and we would divide it by 15 days. Those units kind of like help you work out the problem because days cancel right there. And if we take this number, 376.5, and divide it by 15, we're going to get 25.1. So 25.1 degrees Celsius would be your average temperature over those 15 days. The only reason we had to do that last part is because it asked us for average temperature. You don't always have to like divide there at the end. For a lot of trapezoidal sums, you would have stopped at that 376.5, depending on what they're asking for. Okay, questions? All right, so on the next slide, I have summarized the trapezoidal rule for you. And as long as you have equal subintervals, you can shortcut straight to this. If you have different length subintervals, you have to do the area of each trapezoid separately like we did on the first problem. Okay, so if you have different subintervals, this rule does not work. But if the subintervals are the same, then you can do delta x over 2. That delta x right there is the width of the subinterval. On the last problem, it was your 3, right? And they do the delta x divided by 2, because 1/2 times 3 is the same as 3 divided by 2. So they do delta x divided by 2. And then they've got f of the first interval, or the first endpoint, plus 2 times the second endpoint, third endpoint, fourth, fifth, so on, until you get to the end, and you only count this once. Okay, so this table right here shows the speed of a car in feet per second over 1 minute. We are supposed to use the trapezoidal approximation with 6 sub-intervals to estimate the total distance that the car traveled over the minute shown in the table. Okay, so if we're using trapezoidal rule, if we want to skip straight to the shortcut, we don't have to do the area of every single trapezoid. So what is our delta x? What is our width of our subinterval? 10. You're going up by 10 each time. So we will have 10 divided by 2, or you can think of that as 1/2 times 10. And then what we're going to do is we're going to use that first endpoint right here. This just gets one time, right? All of these in the middle, we're going to do twice. And this one, only once. So it's going to be 0 plus 2 times 15 plus 2 times 24 plus 2 times 31 plus 2 times 45 plus 2 times 52 plus 65. There. And so that saves us a lot of time on doing this, because we don't have to do every trapezoid separately for that. So if we type that into our calculator, get rid of this stuff. We got 5 times 2 times 15 plus 2 times 24 plus 2 times 31 plus 2 times 45 plus 2 times 52 plus 65, and I get 1995. And here, my units, I was finding the area, so I was multiplying my x units by my y units. So that was seconds multiplied by feet per second. And seconds would be like seconds over 1. The seconds cancel. So 1,995 feet is my approximation.
I think it's also kind of easy because you can just look at like the end of the equation. Like when it says, or what it's telling you to do, it says estimate the total distance. It would be.
Right, it does. A lot of these will sort of give away what you're looking for your units as far as the way they ask the question. Again, cannot stress enough, this only works with equal sub-intervals. It will not work if you have different sub-intervals like we had on the walnut. Okay? Questions? All right, let's do a midpoint problem. Okay, I put the table and the graph here to help us a little bit, like picture what's going on here. So this gives us velocity of a car traveling on a straight road from 0 to 50. Table of values is given at 5-second intervals, shown to the, and the graph is also shown. Approximate the area under the curve with a Riemann sum using the midpoints of 5 subintervals of equal length, using correct units explained. So how many subintervals does it look like we have on this table? A lot more than 5, right? It looks like there's probably 10 there. But if they're wanting us to split the distance from 0 to 50 into 5 subintervals, then what's the width of each subinterval? 10. So we've got, what we're doing is we're splitting here at 10, 20, 30, 40, and 50. So even though we have the information to do 10 subintervals, we're only doing 5, which is going to have to be necessary because they asked us for a midpoint Riemann sum. Because if we're doing a midpoint Riemann sum, we do not use the left endpoint or the right endpoint. We use the endpoint right there in the middle. So whenever we draw this rectangle right here, we don't have the rectangle using this point or this point down here or this point up here. We use the one that's at 5. So, like, if we think about that one, we've got a width of 10, and we're multiplying by f of 5, right? So, 10 times f of 5 there. And then we would do our next one, like to draw it in to see what it looks like. Again, width of 10, so I can factor it out. This one would be f of 15. Our next one would be right there at 25 would be our height, so f of 25. This one here would be f of 35 and f of 45 for that last one. Okay, so when we're pulling that from our table, we're like our interval goes from 0 to 10, but we use 12. Our f of 5 is 12 right there. So we got 10 times 12. And then the next interval is from 10 to 20, but we use the number in the middle. That's our 15. So we get 30 there. 20 to 30 is going to be, we'll use 25, which is 70. 30 to 40, we use 35, which will be 81. And then 40 to 50, we use the number in the middle, right there, which is 60. There's a decent chance they'll give you something like this without a calculator. Let's see, that'd be, it's 160 plus 12 is 172 plus 81. It's going to be 253, I think. So we got 10 times 253, which will be 2,530. And this is very similar to the last problem. We're taking feet per second, multiplying it by seconds. This is just going to be feet right here. They don't ask midpoint Riemann sums as often as they ask the left and the right, but they do put them on there sometimes. Okay, questions? Okay, I've got one more thing that I want us to do before we get to our assignment. And that is, I want us to think a little bit more about whether we have an overestimate, underestimate, or overestimate or underestimate for a left and a right Riemann sum. So I have 4 different graphs here. I, on purpose, picked graphs that are, we've got increasing and concave down, increasing and concave up. We've got decreasing and concave down, decreasing and concave up. Okay, and I want us to look at what happens with a left Riemann sum, a right Riemann sum, and a trapezoidal sum. So I'm going to do the first one together, and then I'm going to let you guys look at the rest of those. So if I were doing a left Riemann sum, then I would put my left corner on my graph. I wouldn't even really have a rectangle here. I'd have a rectangle that looks like this. I'd have a rectangle that looks like this. Yeah. We don't usually do Riemann sums, but they can be. Usually the questions that they ask you for Riemann sums are going to be in the first quadrant. They don't usually ask you elsewhere. Technically, you could do it. When we get to like doing actual integration, then they will ask us to do some that are not first quadrant. But for these approximations, you can kind of think of these like the limit definition of a derivative. Like, it's not the best way to do it. We're working up to a better way. So usually it's first quadrant for this. Yeah. Well, definitely quicker. Definitely quicker. There's not too much difficult about finding the area of a bunch of rectangles. It just takes a while. So definitely quicker. And more accurate, because this is still an estimate. This does not give us the exact amount. And we do have to do some limits here in a minute. Or not today, but coming up. So it's a little bit of the same pattern. Estimates aren't too bad. Difficult limit stuff, shortcut that makes everything a little bit faster, sort of like we did with derivatives as well. So if I do a left Riemann sum, do I have an overestimate or an underestimate? Under. Okay, but I'm going to erase this. If I did a right Riemann sum, then I would be putting the right corner of my rectangles on that point. What's that going to give me? Over. And if I did a trapezoidal, so trapezoidal, I would have to use this point and this point. Technically, that's going to be a triangle for that first one, but then once I move forward. What do you think about trapezoidal? I believe that will be under just a little bit. Sometimes that's a little hard to tell because it's pretty good, but I believe that one will be under. So I want you to go through and look at the rest of those for those other graphs real quick. I forgot to cut the recorder back on, Lucas, so here are the answers at least. There's 6 and 7 and 8 and 9 and our conclusions here. Calculus symbol. So when you look at those problems, you are going to have something like this, and you'll have like maybe a 0 to 120 and f of x dx, something like this. This means the area under f of x from 0 to, I guess I should say x equals 0 to x equals 120. So whenever they are giving you that symbol, it's our integral symbol, it means the area under the curve from 0 to 120. So it's asking you to estimate that using different types of left, right, midpoint, and trapezoidal sums for that. So does that make sense there? All right, you're welcome to use the calculator on any of those because they do take a little while without the calculator.